Okay, hello, remote people.
Hey, Dodi.
Hi. Hey.
Dodi.
So I'm just going to get started straight away. Here we are. Okay, so welcome back, everybody, for lecture 5, the end of the first week of these lectures on Axion Cosmology. So what have we covered so far? We've covered particle physics models for axions, production string theory models for axions, initial conditions for axions, production in the early universe by various different methods, and now we can finally start to move on to searching for axions and constraints. I'm going to start today with a relatively lengthy introduction to cosmological perturbation theory, because in lectures 6 and 7 next week, we're going to spend 2 lectures on the CMB. And we're going to use the CMB as a constraint and a link between the QCD axion and inflation to place some quite strong constraints in the relationship between the QCD axion and theories of inflation. And in lecture 6, and then in lecture 7, we're going to place constraints on the ultralight axions from the CMB anisotropies and from large-scale structure perturbations and galaxy formation. In this lecture, we'll finally also start to make formal contact with the equations of motion that have been being used in Jens's lectures on fuzzy dark matter. So you'll see the emergence of the Schrödinger system from a relativistic theory. So yeah, you'll see how that happens, and you'll see the relativistic corrections and why they're important. So let's get started with cosmological perturbations. So the reading for cosmological perturbations, I was introduced to it in this paper by Marsh and Birchinger, which I tell everybody to read if you're interested in cosmological perturbations. This set of notes by Wayne Hu are very useful, especially for the gauge transformations, and of course Dodelson. Okay, so we've seen already the metric in general relativity. This is the line element for Friedman, Robertson, Walker. So G mu nu, oh, sorry, I forgot my mu should be an index here. G mu nu dx mu is just a squared times some spatial metric. A is just the conformal factor for the expansion. And here I've written the metric with the angular diameter distance and the metric on the sphere. We can write a general perturbation to, in this case, I've written it as a perturbation to the inverse metric, with this set of functions here. So A is a perturbation to G00, this should be related to the lapse. G0I has a perturbation B, and Gij, the spatial components of the metric, have these 2 components, HL and HT, where HL is a scalar spatial curvature, and Tij is a trace-free distortion. Okay, so I'm gonna work in 2 gauges because I'm partly following Marsh and Birchinger, but also because these gauges are useful in different places. There's the Newtonian gauge, which makes obvious contact with the non-relativistic theory, the fuzzy dark matter, which we've been talking about. But the synchronous gauge is the one that is normally used to compute things, for example, for the CMB in the code CAM. And I also want to talk a little bit about gauge transformations, because when I derive an important property of the ultralight axions later, their sound speed, I won't use either of these gauges, I'll use another gauge. And so you need to understand the relationship between gauges in cosmological perturbation theory. If you're a student here at Göttingen, you've done an introduction to cosmology, non-relativistic perturbation theory. And here, we're just doing the relativistic extension in GR. So, okay, by definition, in the synchronous gauge, the A and B perturbations are 0, and we consider just perturbations H, I, and J to the spatial metric. And we're concerned here with the scalar modes. I'm not going to talk at all about the vector and tensor modes, but there is a theorem in GR, scalar vector tensor decomposition, that these modes don't mix linearly. So if I create an initial condition that only excites a scalar mode, it does not mix with the vector or tensor modes. And you can write this for the matter components in terms of symmetries of the energy momentum tensor. So we're only going to consider the scalar modes. But this is again an advantage of the synchronous gauge. The synchronous gauge allows you very easily to talk about vector and tensor perturbations, whereas the Newtonian gauge, as it's normally written, only concerns scalar perturbations. Extending the Newtonian gauge to vector and tensor perturbations is not a common thing. So synchronous gauge, much more adaptable in this sense. Okay, so we're concerned with two scalar modes of this tensor H, and we work in Fourier space. So we write Hij in Fourier space in the following way, and these symmetry properties give us the scalar modes. So we have some mode small h, not to be concerned with, not to be confused with the dimensionless Hubble parameter, or Planck's constant, or any other h's lying around, and then this metric potential eta, which appears like this. And you notice that I use tau for conformal time in order not to involve confusion with eta. So here they are, our two scalar potentials, h and eta. And the coordinates for the synchronous gauge are defined, this A and B condition, to follow freely falling observers. This means that the velocity of pressureless matter, for example, CDM, is by definition 0 in this gauge. And we'll kind of return to this later again. And you'll see it many times. For the vector and tensor modes, you can see Marsh and Birchinger of the synchronous gauge. And they're, of course, important for cosmic microwave background, in particular B modes, for which you need to follow the tensors. And we will talk about that, although it won't show the tensor equations of motion. Okay, so the other gauge that I mentioned we will talk about is the Newtonian gauge. Only considering scalar modes, as I mentioned. You have the potentials psi and phi, psi on the time-length part, phi on the space-length part. Phi is the usual Newtonian potential. We'll see this is the thing that appears in Poisson's equation. And psi, however, the appearance on the time-length component is the gauge invariant curvature perturbation. So it's important to be able to compute psi in terms of the synchronous gauge metric perturbations, because psi has a kind of obvious physical interpretation that we're familiar with. These two are equal and opposite in the non-relativistic limit, which we will see. Okay, so the Newtonian gauge is more intuitive for scalar perturbations, but the synchronous gauge is often used in practice. So we need to talk about how to get between them. Gauge transformations. So a gauge transformation in general relativity is just a general coordinate transformation. We go from coordinates x mu to x twiddle mu, which is x mu plus some function of the coordinates psi. And then you can just work out how this affects the metric. The metric is a tensor. You can then work out in terms of derivatives of this function psi what your mu metric potentials are after your coordinate transformation. In order that you satisfy general coordinate invariance, the line element ds squared should be invariant, and we work to first order in perturbations. So we assume that the gauge parameter psi is of order the metric perturbation, and then we expand. And you can find this all worked out in Marsh and Birchinger. And you find the following relationship between the Newtonian potentials and the synchronous gauge potentials. So the Newtonian potentials are related to time derivatives. So primes here are derivatives with respect to conformal time tau. So the Newtonian potential is this function of h plus 6 eta. Well, everything always appears, the Newtonian potentials always depend on h plus 6 eta. Except for eta, which appears directly in front of the Newtonian potential. Okay, so we've got psi and phi, and you can compute them in terms of your synchronous gauge perturbations. This is how you go between the two gauges. We need next the energy momentum tensor. And as I mentioned in the last lecture, it's important to know that the energy momentum tensor is not gauge invariant. The elements of the energy momentum tensor contain the metric potentials and change when you change coordinates because it's a tensor. It has to change its components when you change the coordinate system. Okay, so recall this is the definition of the components. T00 is minus the energy density. Tij, there should be a J lower index there, is delta Ij times the pressure plus some anisotropic contribution. And T0I is rho plus P times V. And again, this is we're just concerned with the scalar perturbations of this object. So working to first order, we expand rho goes to rho bar plus delta rho, P goes to P bar plus delta P. The velocity is already first order. The velocity is already a perturbation. There is no velocity in the Friedman background, and there is no sigma in the Friedman background, so they're already first order. That's what I said here. So we can then define the following useful quantities because they appear in the equations of motion this way. The overdensity is just delta rho over rho bar. This is the common thing that you see everywhere in the matter power spectrum that we'll talk about. Theta is the dimensionless heat flux. So rho bar plus P bar times theta is just I times the gradient of T0J. So K is just IK is just gradient operator in Fourier space. So rho bar plus P bar theta is just gradient rho plus PV. And then this scalar anisotropic stress, sigma, is this following contraction of sigma ij. This is the thing that means that sigma is the component of Tij that only acts on the scalar perturbations. If you look at, say, the scalar vector tensor decomposition of the Einstein tensor in Dogelson. Okay, this is just what I've said appearing on the slide. Delta is the overdensity, theta is the heat flux, sigma is the anisotropic stress. As I said, the energy momentum tensor is a tensor, so it has to transform in the coordinate transformations. So T in the twiddle coordinate system is T in your original coordinate system times the derivative of the coordinates, of the new coordinates with respect to the old coordinates, giving you this following tensor. And all the indices should be in the right places if I've done it correctly. So we define, in order to work out how my energy momentum tensor transforms, following Moore and Bertschinger, you define the following gauge transform variable. So x twiddle, alpha is x twiddle 0 minus x 0. And we write this in terms of the synchronous gauge metric perturbations. So the tilde coordinates are in the synchronous gauge, and the untilde coordinates are in the Newtonian gauge. Sorry, there should be a bracket here on the delta sin. So now I can write each of my components of the metric of the energy momentum tensor in the synchronous gauge in terms of its components in the sorry, con here means conformal Newtonian gauge. Sorry for this mess of notation here. I should have written nu or con everywhere here. Nu and con are conformal Newtonian gauge. So for example, the overdensity in the synchronous gauge is the overdensity in the conformal Newtonian gauge minus alpha rho bar over P bar, theta alpha K squared, delta P alpha P bar, and the scalar anisotropic stress is the same in both gauges. So, okay, what are the Einstein equations? So, you work through, you write down your metric, you work out your Einstein tensor, you write down its non-zero components, you work out how they're sourced by components of the energy momentum tensor, and you find these equations of motion. So in the synchronous gauge, the first equation is the basically the equivalent of the Poisson equation. So we saw the relationship between the Newtonian potential and eta. So they are proportional with this extra factor here, which is more from the gauge transformation. So we recognize in the first equation something that's looking like the Poisson equation. Laplacian acting on eta, sourced by the energy density. And then we have all our other equations, one sourced by theta, one sourced by pressure, and then one sourced by the scalar anisotropic stress. Newtonian Einstein equations. So now, remembering that we're relativistic, we don't have just plain Poisson's equation. We have Poisson's equation plus extra relativistic terms to do with the time dependence of the potentials and the expansion of the universe and things happening at the horizon. We've got the usual Poisson equation, k squared phi minus 4 pi ga squared delta rho. Then we have this term that involves time derivatives of the potential and things including Hubble. A prime over A is the conformal Hubble rate. To remind you that primes are derivatives with respect to conformal time. Then again, we have these equations sourced by theta, p, and sigma. The important thing for the Newtonian gauge to notice, especially for the non-relativistic limit, is the last one. So the last one, phi minus psi, is sourced by the scalar anisotropic stress. If the scalar anisotropic stress vanishes, therefore phi is equal to psi. So that's what's normally used when you saw Jens derive the equations of motion for fuzzy dark matter at the beginning of his first lecture. His Newtonian metric only had one potential in it, and that's because in the non-relativistic limit there is no scalar anisotropic stress. But the anisotropic stress is sourced by photons. Higher moments of the photon distribution function are non-vanishing and source this. It's sourced by neutrinos while they're relativistic, and it's also sourced at second order by scalar field perturbations. Then we have all of these other usual things. Okay, so things involving time derivatives of the potential can be seen to be relativistic corrections. The potential only varies on scales of order the horizon on time scales of order Hubble. So if you ignore the horizon, these terms drop out. And you can see that by inspecting these equations, working out what order everything is. And the potentials are equal if the anisotropic stress vanishes, as I said. Okay, so what are the equations of motion for cold dark matter? The reason I'm showing you all of this is because I'm going to write down results about the CMB in the next 2 lectures, and I just want you to understand like where the equations of motion come from, what kind of things you solve, what it looks like under the hood when you solve these things. Okay, so equation of motion for cold dark matter in synchronous gauge has no velocity. Theta c is 0, so we only have one equation. Delta c prime is minus a half h prime. This makes synchronous gauge very easy for cold dark matter solutions, even in the relativistic case. Whereas in the Newtonian gauge, we have the non-relativistic continuity equation, delta c prime equals minus theta c, plus a relativistic correction to do with the time dependence of the potential. Similarly, we have something that looks like the Euler equation for theta c prime, sourced by the Laplacian of the curvature perturbation. And again, this is not the Newtonian potential in the case where you've got anisotropic stress. We're going to be interested in CMB perturbations, and something you know, or you may know about the CMB is that it has these baryon acoustic oscillations, and baryon acoustic oscillations up until the time where recombination happens, and then free streaming of photons. Where do they come from? They come from the equations of motion of the baryon photon plasma. So I'm going to neglect, just for the simplicity of the slides, I'm going to neglect the anisotropic stress. I'm going to neglect higher moments in the Boltzmann hierarchy. So I'm going to truncate my photon hierarchy of moments at the first moment. So I have an equation of motion for the photon over density. Looks just like the CDM one, but with a different factor, minus 4/3 here from the photon equation of state, which is a third because it's relativistic. And I have this equation for theta gamma prime, the photon velocity perturbation, and it is this couples the photons to the baryons via the Thomson scattering term. So this is a key thing. Baryons look like cold dark matter because they have their non-relativistic equation of state 0. on background. But then we have the baryon perturbation. The baryon velocity perturbation looks very different. Baryon velocity perturbation has a sound speed for baryons, which depends on the baryon temperature. And then it was also coupled to the photons via the Thomson scattering term. Okay, so if there is tight coupling, if this term is large, then the photon and baryon velocities are fixed to be the same, and you have a single fluid moving together. This is what we mean by photon baryon plasma. And then this single fluid will have a sound speed, and the sound waves can propagate in this combined fluid when they are tightly coupled, when it is tightly coupled. The coupling, however, depends on the free electron density. So you have to be able to compute the free electron density in your plasma. This is something that has to sit on top of solving these equations. You need a separate thing that computes the free electron density, something that either involves recombination or reionization. Recombination in the early universe, these sound waves only once the free electron density drops to 0, when hydrogen recombines, there is no coupling between photons and baryons anymore. Sound waves stop propagating, photons freely stream, and the baryon sound speed also drops to 0. But then there is also another contribution to this that arises at late times due to reionization. So this is just what I said again. Baryon sound speed comes from the baryon temperature, and free electron density needs to be computed using a code for recombination or reionization. Recombination being the important thing in the early universe. Okay, so now we need initial conditions for this system of equations. So we're going to have photons, baryons, cold dark matter. I'll add in the axions later. In general, neutrinos, anything else you want to add in, dark energy perturbations, anything like that. They need initial conditions, because the initial conditions tell you in what state you began. You only want to excite certain modes of this system. This system has many modes because it has many degrees of freedom. You only want to excite certain modes corresponding to your theory of the early universe. Or rather, you want to be able to constrain what modes were there. And this is the importance of the CMB in the next lecture. So, we want to set, so that we have no transients from the wrong mode, we want to set our initial conditions such that they satisfy Einstein's equations for that mode at early times. So we do an expansion. So we know from our discussion of inflation a few lectures ago that during inflation, the causal horizon shrinks, which means modes leave the horizon. Then after inflation, the horizon starts to grow again, so modes re-enter the horizon. But superhorizon modes do not evolve, or have no gauge invariant evolution. So we can fix our initial conditions when they are superhorizon. If we're talking about the late universe, the post-inflation universe, we fix our initial conditions when they're superhorizon. Then when the horizon catches up with them, that's when the evolution will begin. So so we just do a power series expansion of all of our functions in the limit that k tau is very small. So this is our small parameter. Tau is the size of the horizon in conformal time. And for the background evolution, I'll further assume that the conformal time itself is very small, which just means that we need the scale factor to be small. We need to be close to the, we need to be very deep inside the radiation era, if you like. Okay, so how do we set these initial conditions? There is one mode, the adiabatic mode, which is very important. The adiabatic mode has all perturbations seeded just by scalar curvature. You begin with a single perturbation coming from the inflaton, or anything, just that there is one thing at the beginning of the universe. Could be the inflaton, could be the bouncing universaton, or whatever you like, but one thing, and that decays into everything else, and thus everything is seeded from the curvature perturbation in this first object. This means that the overdensities in all of your different species, I and J, are related by the following condition. So 1 plus Wj delta I equals 1 plus Wi delta J. So for example, in terms of the in terms of the Newtonian gauge, you get the following condition. So delta gamma is sourced by the curvature. Theta in every species is just given by this lowest order relationship to the curvature. Linear evolution means we can just choose the curvature to be 1, solve the equations with curvature of 1, then multiply at the end by the initial conditions. You'll see this happen again and again. And then this relationship, this 1 plus Wj, 1 plus Wi, means we can relate, say, that delta in cold dark matter will be, okay, so let's have a look. W cold dark matter is 0. Let's call I cold dark matter. So delta C will be delta gamma divided by 1 plus W of gamma. W of gamma is a third, so delta cold dark matter is 3/4 delta gamma in the adiabatic mode. So delta cold dark matter will just be minus 3/2 times the curvature perturbation. Okay, this is the adiabatic mode. Another thing you notice is that if the equation of state of a given species is -1, if it's a perfect cosmological constant, you can have no overdensity. Delta I is identically 0. This is an interesting thing, as we'll see, for the generation of initial conditions for ultralight axions. They begin when W is very close to -1. So in the adiabatic mode, they have almost 0 perturbations initially, but we'll see that they can still match cold dark matter once this transition in the equation of state happens and they match it dynamically. Okay, so just to show you that we can do the same thing in synchronous gauge. And in synchronous gauge, eta plays a similar role to the curvature perturbation in the Newtonian gauge. So the adiabatic mode, to conform with Newtonian gauge, is just psi equals 1. In synchronous gauge is eta equals 1 plus order k tau squared. So the adiabatic mode is the eta mode of the perturbations, and then everything else is higher order, but multiplied by this eta that you just choose. And there are other modes, obviously, that there are modes for every degree of freedom of your system. The adiabatic mode is kind of like the trace mode or something. So isocurvature modes, or so-called entropy modes, they involve a perturbation Sij between the curvature in species I and the curvature in species J, where they are defined in the following way. So the curvature from one species is the total curvature minus h times solar density, and the total curvature perturbation here, zeta, is just this weighted sum of the individuals. So a mode like this entropy mode, carries 0 total curvature, zeta. And it's quite easy to see here in synchronous gauge what these modes are. So you can have a isocurvature mode for every degree of freedom. And it's easiest to, every degree of freedom in your fluid, because we've already said the adiabatic mode is basically the eta degree of freedom. So then for all of our other modes in our fluid, we have isocurvature modes. So we can have I-type density isocurvature and I-type velocity isocurvature. And that just means that I start with delta I equals 1 for the density isocurvature, or theta I equals k for velocity type isocurvature. So this is, for example, this is all done really nicely in this paper by Booker, Mudley, and Torak. And we will come across, I'll show you plots of what all of these do to the CMB in the next lecture. Because these are different modes, they all have different transfer functions, and we'll talk about transfer functions today, and also in lecture 6. So for your isocurvature modes, all the other species are excited only at higher order, and for example, the initial condition for eta, the thing that's like the curvature, is a higher order quantity. So at first order, there is no curvature. But of course, everything's coupled, so eventually you generate all kinds of other things. The neutrino velocity isocurvature, by the way, is a very interesting mode, but there's no early universe theory that excites it, but it has it's quite interesting in terms of its CMB spectrum. Okay, so we're nearly able to start our system off. We need our initial condition. So because the system is linear, the leading mode, which I could just set to 1 before, can just be factored out. And then at the end, I just multiply by the initial condition of the object. It's the initial conditions that are stochastic variables. It's the initial conditions that are random variables, and they're affected by any ensemble averages or related to spatial averages by the ergodicity. So all the correlations in a linear system are accounted for in the initial data because there is no mode mixing. So this is all really just computing, if you like, for a time-dependent system. You're just computing the propagators, if you want. And also all of the statistical properties are accounted for in the initial data. And to kind of speak back to what we heard about this morning in the Jan's lectures from Jan, when you do anything non-linear, you also need initial conditions. And the non-linear thing, when you do a simulation, an n-body simulation or anything, you of course need to do what I'm doing now to give you your initial conditions. So we're always moving kind of one step back. Okay? So I'm just going to write what I just said out in symbols. So consider some variable phi. This is, for this slide, not the Axion field. I can write phi for some mode k as my initial stochastic random variable times some transfer function phi tilde. So the initial random variable just factors out because it's linear. And I can now write a normalized evolution. This is going to give me my transfer functions. So for example, I can then define the power spectrum between two different variables, 1 and 2, in the following way with angle brackets, where the angle brackets are now ensemble averages over my stochastic initial conditions. So here P12 is just defined by the following. I'm assuming isotropy, so I only depend on the absolute value of k. So delta P12 is 2 pi cubed delta Dirac delta function, k minus k prime, phi 1, phi 2. But the ensemble averages only act on the random variables and the initial conditions, like this. So then I just notice now this is just the power spectrum of the initial conditions times some normalized transfer function which I can compute, which has no stochastic properties. So that's this. So P12 is just the initial power spectrum times my normalized evolution. So I can compute this this transfer function numerically by solving this coupled system with the normalized initial conditions. And the initial power spectrum comes, for example, from inflation. So this is now, we can now make our first kind of rough contact with observables. So this is something you might try and observe. This is the matter power spectrum. And you can infer the matter power spectrum. So from what we just wrote down, it's just the matter over density squared times the initial matter power spectrum. So it's just some transfer function times the initial matter power spectrum. And you can estimate this from all kinds of different observables. Just for those here, I'm just going to move my square there. So this is the matter power spectrum. All the estimates compiled in the recent Planck release. You can estimate this thing from the temperature evolution of the CMB, polarization, lensing, phi. And you can also estimate the matter power spectrum from galaxy power spectra. But projecting it onto all of these things don't measure this directly. Every single one has been put onto this plot for measuring something else. So it's a little bit misleading. But for example, the Lyman Forest and Dark Energy Survey cosmic shear are projected onto here. And we noticed, for example, that the cosmic shear measures scales quite close to the Lyman Forest, which is why I'm quite interested in it. Okay, so this is the kind of thing you talk about observing. If everything was nice and linear, all you need to compute was your transfer functions, and then you could constrain both the evolution, the things that are involved in making your transfer function, and separately, your modes of your initial conditions. There's an important thing to come back to our discussion of gauge. So delta is not gauge invariant. I stressed this earlier. So this thing is not an observable because it's not gauge invariant. However, our gauge terms all involved time derivatives of potentials, factors of Hubble, and factors of 1 over k. So they're all things that decay on sub-horizon scales. So all gauges agree on sub-horizon scales, as they should. All gauges agree in the non-relativistic limit. Gauge invariance in general relativity is a relativistic thing. So you can compute this in whatever gauge you want and compare to observations as long as you're on non-relativistic small scales. Gauge-dependent things, however, do appear on ultra-large scales. And if you want to talk about measuring the power spectrum on very large scales, it's not just given by delta squared. It has to have other contributions. In the CMB, and I'll show you this in the next lecture, we're very familiar with the equivalent gauge-dependent terms. The CMB on ultra-large scales has to have Doppler, Sachs-Wolf, gravitational redshift, all of these things combined into your observable delta T over T, which is gauge invariant. There are equivalent expressions for the matter power. So ultra-large scales, the matter power spectrum, we always see the matter power spectrum plotted as looking a certain way, but it only looks that way as this kind of power law that just decays on small k. That is something that is specific to synchronous gauge. The observables, you have to compute your observable for whatever you're looking at. That is gauge invariant. Okay, so we've done all that matter, photons, photon baryon plasma. We're now just going to add axions into that mix, into that standard story. So here the reading would be chapter 4 in my review. Wayne Hu's paper on generalized dark matter. It's very good in this regard. I'm going to use results from Huang and No, and a lot of this has gone through in more detail in my paper with René Roger-Dangren and Pedro Ferreira from 2014. So we're going to start with our background evolution. We discussed this in the last lecture. This is the thing that gives you, I shouldn't have a K if I'm doing background evolution here. Forget the K. This is just the Klein-Gordon equation in conformal time. We saw it in physical time in the last lecture. And we used it to compute the Lorentz density. And note here that in conformal time, the coefficient of the friction term changes. It's not 3H, it's 2 conformal H. So then we can work out the equation of motion for the perturbation through the Axion field. So we start with our Klein-Gordon equation, we write down box, we write down phi, the field is equal to phi bar, the background field plus delta phi. Equation of motion for phi bar is gauge independent because it's just the background, the Friedmann background. The equation of motion for the perturbations is gauge dependent because what is delta phi depends on your time slicing whether or not there is an axion perturbation or not. So the equation, so the Klein-Gordon equation has this kind of normal term that looks like box, with now the k squared should be there because we're gradients of this field perturbation delta phi, but the source depends on what gauge you're in. So here in the synchronous gauge, the source is related to the time derivative of the background field and the time derivative of the synchronous gauge metric perturbation. Okay. So we can also write it down in Newtonian gauge. We have the same thing that looks like box, but now we have these terms here on the right-hand side related to the Newtonian potential. This one would be the kind of usual Poisson source, the rightmost term, but the first term is like a relativistic source related to time dependence and potential. I like the way the synchronous gauge shows us what's going on here because you can see that there is only a source for the perturbations when the background field has a time dependence. This is nice. So I said before that the Axion field, so we know that its background equation of state is close to -1 at early times when it's overdamped. That means that phi prime is almost 0, and in the adiabatic mode, delta phi is almost 0, plus corrections of order the slow roll. delta phi will also not grow until phi prime begins to become non-zero. So you can see very obviously that perturbations in the Axion field can only begin to grow once the background field has begun oscillating. So the fluctuations only start to grow once the background field begins to behave like matter, once it goes from W minus 1 to W0. So this is all very good. Why can't we just solve the Klein-Gordon equation coupled to stick the Klein-Gordon equation into our system before and just solve it? The problem is, to use the phrase that Jan used before in relation to the Schrodinger equation, it's a stiff system. It involves multiple time scales. So the time dependence introduces hierarchies of scale. So for example, in this slide here, M and H, M is a constant, but H falls over time. So at first you have just a single time scale, the evolution with respect to Hubble, but then when Hubble drops below the mass, the field begins to oscillate, and the oscillations happen on a time scale that is much shorter than the expansion time. So then you have a stiff system. So this introduces hierarchies, and the whole problem with cosmological perturbation theory is dealing with these hierarchies. So for the axions, the field equations of oscillations, when m squared plus k squared over a squared is greater than Hubble. So that's just looking at the evolution operator on the left-hand side of the perturbations and changing to physical time rather than conformal time. So you see that the field begins to oscillate when this condition is met between the mass and the wave number. Again, we saw this type of behavior for the axion field in the absence of gravity. Also, when we talked about strings last time, that wave number is at that mass. So they are raised, so the field oscillates and goes down to a zero once it enters the horizon. So we can use this oscillation to help us deal with the hierarchies using the WKB approximation. So once the oscillation period, so we see from this that the oscillation period is guaranteed to be smaller than 1 over h. So the frequency is this thing here. So the period is 1 over m squared plus k squared over a squared, and that's shorter than 1 over h. So to study structure formation, we need to follow modes that from horizon entry in the radiation dominated era up to redshift of 10 to the 7. This corresponds to, physical scales of 1 to 10 in the megaparsecs. Down to today, redshift 0, and this is where the huge hierarchies come from. The difference in the Hubble rate from redshift 10 to the 7 to redshift 0. So brute force solution of the Klein-Gordon equation is not really feasible, so we need to work on it. What are we going to do? This is the solution strategy that we adopted in Axion CAM. Axion CAM is a modification to the usual CMB code CAM, which you use to compute CMB anisotropies, but also to compute initial conditions for n-body simulations. This is the strategy we use to add axions into that standard bit of code. So you have to solve the, so what we do is we solve the Klein-Gordon equation up until that onset of oscillations in the background. So the oscillations in the higher frequencies, we have to deal with by brute force. We wait until everything has started oscillating, including the background, and then start to use a WKB solution on the background. What do I say here? In reality, choose carefully. Oh yeah, so this is approximate this condition. When do you make this switch? In reality, you have to choosing this switch involves a little bit of care. You might want to follow the first few oscillations of your field to improve the accuracy. If you're using a potential that isn't m squared phi squared, you also will have to follow the first few oscillations until you're in the harmonic regime, just like in the case of the Reynolds density. So in reality, you have to be a little bit careful, and this has hindered us from extending Axion CAM to potentials beyond quadratic, at least in public versions, because of this, the care you have to take with the background evolution. Okay, so solve the Klein-Gordon equation up to some point. just like we did actually for the amount density. And then after that, switch to WKB. But now we're going to do the WKB on the perturbations as well as on the background field. This is just like the density. So we write our background field as our envelope function, which just means that density goes like 1 over a cubed times some amplitude, phi plus, phi minus, for the cosine and sine parts of this. This just accounts for an arbitrary phase. We do the same thing for the perturbations, but we don't know how the envelope function of the perturbation evolves. So we allow the envelope function delta phi plus, delta phi minus to carry the wave number of delta phi, and then to have some arbitrary time dependence, some arbitrary envelope function, because that's what we want to solve for, the time dependence of the envelope. We use these solutions to fix the background equation of state. So we know here that the background equation of state W, which is P over rho, will be 0. And then we also need to use this to find the sound speed of some effective fluid for the perturbations. So just like for the background, we switch to a single fluid with the equation of state. We try and do the same trick for the perturbations. And then we just solve fluid equations for the axion over density and axion velocity. This is one step before the Madelung transformation that we used on the Schrodinger equation in Jens's lectures. This is only integrating out the relativistic oscillations on the Compton scale M. This is going from Klein-Gordon to Schrodinger, if you like, but just at first order in perturbations. Okay, so what are the fluid variables for the axiom? So we need to recall in the background, this is the energy density and the pressure in terms of the background field phi bar, and the derivatives with respect to physical time t. The equation of state fixes the evolution of the background energy density from the continuity equation. W is P bar over rho bar. You substitute in that WKB solution and average over timescales larger than 1 over m. Then the average of the equation of state and the average of its time derivative, of its conformal time derivative, both become 0 when averaged. So A, and this applies when A is larger than A osc, which I introduced last time, and for a harmonic potential V for the axiom. So this is just what we saw last time. On late times, the axiom behaves like pressureless matter in the background. The important thing is that it does not behave like pressureless matter in the perturbations. So first of all, we need to find the energy density, the pressure, and the velocity perturbation. At first order, in the fluctuation delta phi and in an arbitrary gauge, they take the following form: delta rho, delta p, and v. So you notice that delta rho and delta p depend on the gauge, as does the velocity. It is very easy to show that, okay, so you can choose a gauge where there are just no axion fluctuations delta phi. That doesn't mean the energy density in the axions will have no perturbations in those gauges, because A will in general be non-zero. But you can show in the gauge where delta phi equals 0 that the sound speed, which is delta p over delta rho, is just trivially 1. So we look at this, look at these two lines here, delta p, delta rho. If we go into the gauge where delta phi is equal to 0, take the ratio, then the sound speed in this gauge, delta p over delta rho, is 1. That's why people will often say to you, the sound speed of a canonically normalized scalar field is 1. They mean the sound speed in this gauge. And this is a very useful gauge, and it's used for inflation calculations. However, it's not a very useful gauge for cosmological evolution. That's because once the background field begins oscillating, the relationship between this gauge and the Newtonian gauge involves these rapidly oscillating terms. So using this result, sound speed equals to 1, doesn't make your life all that much easier for following gravitational collapse of a rapidly oscillating field, but it is very useful for a slowly rolling field like the photon. So we need to choose a better gauge. A better gauge to work out what's going on is the so-called Axion co-moving gauge. In this gauge, we set V equal to B. So we make this choice here, so that we have now a relationship. If I substitute in my WKB expansions for phi bar and delta phi, I can relate the plus and minus components and fix the phase of my Axion evolution. So I substitute here, I find delta phi minus times phi bar plus, there's delta phi plus times phi bar minus. In this case, we work up the equation of motion for the Axion fluid just from the Klein-Gordon equation. This is literally just substituting in our definitions, and it takes the following form, and it looks somewhat like the synchronous gauge. So this is a co-moving gauge. It is not co-moving with the dark matter fluid, as the synchronous gauge is with the cold dark matter fluid, but it's co-moving with the axions. So there's some fluctuation H prime. And then it looks like a fluid with this nice sound speed here, which is just delta P over delta rho in this gauge. And you can work out what that is. Using our WKB ansatz in this gauge and taking the time average, you can actually compute this sound speed term, and it takes the following nice closed form, derived very nicely in this paper that I referred to before by Huang and No. So you can see very nicely here that this is the manifestation and perturbation theory of the quantum pressure. So this now looks very much like the Madelung equations that we saw before. Sorry, there should be an equals sign. One of these minuses on the phi prime equation should be an equals, obviously. There's a typo there. Either the first minus sign or the second minus sign. And I think it's the first one. Okay? So, this looks very much like the Madelung equations, but with some relativistic bits stuck on to do with W prime and 3H here. But you see that pressure, sound speed, opposes gravity. The sound speed here comes from k squared gradients of the energy density delta. So this is the appearance of the gradient energy in the Klein-Gordon equation. And we have different powers of T and K because we're in some kind of non-relativistic limit. So this is very nice, but we can't just substitute this sound speed into here and solve these equations because our code works in synchronous gauge. So we have to take a gauge transformation from the Axion co-moving gauge, where the sound speed takes a very nice form, to the synchronous gauge. Okay, when we do that, we get some extra terms. So the sound speed now is still the Axion co-moving gauge sound speed with that nice closed form expression that I had. But compared to the previous equations, this is H in the Axion co-moving gauge, I get an additional term here, and the last term on the first line, minus 9 conformal H squared C squared theta A over K squared, which makes this look different than the equation for an ideal fluid in this gauge. I've also substituted in here the background equation of state W equals 0 and W prime equals 0. So this is after my boost to the synchronous gauge. And the equivalent Euler equation for theta contains now the sound speed, as you would expect, but also an additional relativistic correction due to the gauge transformation. So the non-canonical fluid terms on the right-hand side account for this gauge transformation and this sound speed coming from not the gauge that we're actually looking at. A numerical solution of this system, doing these switches in a self-consistent way, solving the background equation up till some point, and then switching to this WKB solution, This has been implemented in the full cosmological standard model, coupled to the photon barrier plasma, all of that, in Axion CAM, which you can get from Dan Grinn's GitHub. And we're working on, we will start working on at some point, a new version of this. So this is in the old CAM, that's a Fortran code, standalone, but new CAM is Python module, and so we're going to work on integrating Axion CAM into CAM version 1.0. And this is also based on a relatively old version of CAM, so if you're comparing codes, just kind of be careful about versioning. Okay, so we can use this to solve the evolution of the Axion field in the adiabatic mode. And this is now the start of seeing numerical evolution. Okay, so this is the evolution of a single overdensity, of an overdensity delta with some arbitrary wave number k that I've chosen to be small. So I'm looking at just the large scale evolution of delta, where you can neglect the sound speed. The dotted line is the evolution of a cold dark matter perturbation at this wave number. And it just grows with the scale factor, and it changes the shape of its growth around matter radiation equality, redshift 10, scale factor 10 to minus 3. The Axion perturbation, as I pointed out in the adiabatic mode, should be almost 0 because the equation of state is almost -1. It shouldn't be exactly 0, and you have to include slow roll corrections to this to get everything to be consistent. But it starts off with some very, very small amplitude. However, remembering in the synchronous gauge, the source of the Axion perturbation starts to switch on when the background field starts to roll. So as the background field starts to roll down the potential and picks up speed, so the source for the perturbation grows. Then once the background field starts to oscillate, we switch with WKB, and the Axion solution perfectly locks on to the CDM solution on super horizon scales. This is as it should be, because if I just started my whole evolution here at say A of 10 to the minus 5, the Axion is still super horizon. It shouldn't remember that it came from having a different equation of state. I just say I have a field with equation of state 0. I start off in the adiabatic mode at super horizon scales. It should exactly match CDM. And you see here for different Axion masses, here I choose them very small because these are the masses where we can constrain the energy density using the CMB, as we will see next time. I choose masses 10 to the minus 24, 25, 26. And as I make the mass smaller, this transition moves to later scale factors. Okay, great. Let's look at now the evolution at a fixed Axion mass, but for different K modes. So small k, over the horizon, we have the evolution we saw before, comes up, catches up. Here the normalization of delta is arbitrary, I haven't multiplied by the initial power spectrum. And then the different colored lines are for successively larger values of k, going to smaller and smaller scales. On small scales, the sound speed is a little bit important. So for this k of 0.1, the sound speed is just competing with the gravitational attraction, and these are some slightly suppressed density perturbation. But on very large k, on very small scales, the sound speed is dominant over the gravitational collapse and leads to oscillations, acoustic oscillations in the Axion fluid, and a very suppressed density perturbation between the Axion and solid and the equivalent cold dot matter mode in dot. So on smaller scales, the Axion over density is suppressed compared to cold dot matter. But this is from a full solution of the coupled system. Is the way we should be able to understand this in a simpler situation and analytically. So let's look at the linear growth. So we're going to study a simple exact solution of our WKB system. And this is where really things are going to start looking like the perturbed version of the Schrödinger-Poisson equation and the Madelung equations. So we're going to take the sub-horizon limit in the Newtonian gauge in physical time, and we have the Poisson equation. So I've set phi equal to psi, and I've assumed that the time derivatives of phi are suppressed by the relative size of the mode compared to the horizon. Then the equations of motion for the axion look like a normal fluid that you'd be very familiar with from, for example, Peacock. Here's the Euler equation. Theta dot is minus h theta, plus a sound speed term, plus a source due to Newtonian potential. And here I am keeping in my gauge terms from before, going from this gauge to the Newtonian gauge. Then I have delta dot with the usual continuity equation. I further drop these terms in the non-relativistic limit, and that is because h is much smaller than the mass, and k is also much smaller than the axion mass. So I don't want to be on scales close to the Compton wavelength, because otherwise I would have to include all the relativistic effects. So I drop these two terms, and then I can combine these two equations into a single second order equation for delta, valid on sub-horizon scales in any gauge. And it looks like this. So I have second time derivative of delta, some Hubble friction, some sound speed term, and some density source. If I further assume that the world is completely dominated by axion dark matter, I want axions to be of dark matter in this case, fuzzy dark matter over dark matter, then I can replace phi just by the axion over density itself. And now I have the nice normal familiar Jeans equation. Applying the Friedmann equation, I can rewrite the second term, the gravitational source, just in terms of, I know the time evolution of this rho bar, and I can also make a change of variables from d by dt to d by dA. And this allows me to solve for the famous growing mode. So in the limit that sound speed goes to 0, so for axions small k, or in the cold dark matter limit, which would apply to the QCD axion here, k much smaller than this gene scale that I will talk about here shortly, I can just solve for the evolution of delta as a function of a. It is some constant times a plus some other constant times a to the minus 3/2. The evolution of CDM on sub-horizon scales in the matter-dominated era is completely scale independent. CDM has scale independent linear growth. The second mode is the decaying mode, and we choose our initial conditions such that we live in the growing mode. The decaying mode, just like the iso-curvature modes, is something that you can look for the presence of in the CMB, but it is normally neglected simply because its amplitude goes to 0. It's a transient, even if it's there. Okay, this is just what I said. We assume the growing mode. Using the non-relativistic limit of the sound speed, so I basically dropped the denominator on the expression for the sound speed before. So this should be CS squared. CS squared is k squared over 4m squared a squared. You can substitute this this expression for c squared into the equation of motion here, and that also admits an exact solution, somewhat remarkably, but maybe not. But you just ask Mathematica and it gives you an exact solution. An exact solution for the linear growth for axions in the non-relativistic limit. It looks like this. It's not particularly enlightening when you stare at the form of the solution. Only when you plot the solutions is it enlightening. There are two modes again, B plus, B minus. They depend on scale factor, but they also depend on wave number k. And they depend on k, the wave number k relative to this scale, geometric mean of the axion mass in the Hubble scale. And we'll get some intuition for this in just a minute. So what do they look like? B minus, for small k, looks like the decaying mode, a to the minus 3/2. For some medium k, it oscillates and then joins the decaying mode. And for very high k, it just undergoes harmonic oscillations. The growing mode shows all the behavior that we saw before in the numerical solutions. For low K, it just grows proportional to A, like cold dark matter would. For medium K, it has some oscillations, and then will come out with a slightly suppressed amplitude, but grow with cold dark matter. And for high K, we have acoustic oscillations. This leads us on to the gene scale, which is really this is where we're going to jump off for constraints from galaxy formation in lecture 7, so it's very important. So with pressure, the growth is scale dependent, that's what we just saw. The gene scale separates the growth and oscillation. So we look at our linear growth equation, and we see why this happens. When the sound speed term dominates, this is just the equation of motion for a damped oscillator. But when the density term dominates, this has instabilities and has growing modes. So there is clearly a particular K where this term vanishes that separates growth and oscillation. This K is called the gene scale, or the gene's wave number. And we find it by just equating these two terms, substitute in our form for c squared of kj. We can solve for the gene's wave number, and it's the following value. So kj is 66.5 inverse megaparsecs times this dependence on the scale factor, axion density and axion mass. We notice now that if you substitute in what Hubble is in the omega a squared, you see that our k twiddle in the previous exact solution is just proportional to k over kj. So omega a h squared goes like, to the quarter goes like h to the half. Okay, so this was the scale that was playing a role in our exact solution. Let's try and get a little bit of intuition for this, just because I think it's helpful to have something more than just the dry formal stuff. But actually, let me say one more thing. This form of k squared, this form of c squared, this non-relativistic form for c squared, as it appears in the linear growth equation in the non-relativistic limit, here, this is exactly what you would get if you took the Madelung equation and expanded it for first order perturbations and moved to k space. So the weird quantum pressure, this grad squared of square root rho over square root rho, in Madelung form is exactly this. So one way of deriving this non-relativistic sound speed for the linear modes is start from Schrodinger Poisson and work to first order of perturbations. Or if you like, but before we had all of the relativistic stuff for this, for the linear perturbations. Okay, so that's one way of getting why, like, what's the linear, what's the gene scale? The gene scale is the scale at which quantum pressure starts to dominate, if you want to use that language. But there's another way to get intuition for it, which I find it intuitive. So consider an observer and an axion moving away from one another on trajectories following the Hubble flow. So here's our observer, Edwin Hubble, surveying the pipe, and here's our axion moving away from him. They're separated by some distance r, and the axion is moving with the Hubble flow. So its velocity away from Edwin is just the Hubble constant times the separation. Poor old Hubble here can't localize the axion. He can't tell what it's doing. He can't tell whether it's bound into structure or not. If their separation is smaller than the de Broglie wavelength. So if he's within the de Broglie wavelength of the axion, he can't tell what it's doing. It can't be forming any gravitational structure. So if the separation is larger than the de Broglie wavelength, this axion cannot be, as far as Hubble is concerned, involved in any kind of localized structure. So if the radius is smaller than Prince de Broglie here, the axion won't be forming any structure. But as the axion moves further away, as r gets bigger, the velocity increases. So Prince de Broglie here gets smaller. So the wavelength decreases as you move further away. And if we say, well, when can Hubble exactly start to localize the axion? He will exactly be able to localize it when he and the axion are separated by when the separation is exactly the de Broglie wavelength, and this corresponds to separation by exactly the Jeans length. So if we set the radius that they are separated by to be equal to the de Broglie wavelength, then James Jeans here is equal to Louis de Broglie. The Jeans scale is 1 over Rj is equal to lambda de Broglie, which is 1 over m times h times Rj, v equals h times Rj, which is 1 over the square root of m times h. So this Jeans scale, the geometric mean of the mass in the Hubble, can just emerge in this way intuitively. Okay, so why is this useful? This is very useful for getting constraints on fuzzy dark matter. Modes with k less than kj grow proportional to grow like the linear growth, but modes with greater than kj oscillate. Growth essentially starts at matter radiation equality. And so the Jeans scale equality defines the scale where CDM, cold dark matter and axion dark matter deviate. If your k is larger than the Jeans scale equality, all of a sudden equality, everything starts growing and gets away from you. So the Jeans scale equality separates those scales that are going to just look like CDM, because we saw the large scales, axions just lock onto CDM, they don't care, compared to those that are suppressed. So we just evaluate our expression before, substituting in the redshift of matter radiation equality, A at A equality, and we find the Jeans wave number at equality is about 9 inverse megaparsecs times all of these factors. We can try and express this because we know what the matter power spectrum looks like for CDM. That's the thing I plotted before. We can express this as another transfer function that says what's the ratio between the axion evolution and the cold dark matter evolution. We define this to be some other transfer function, T of k, and we can fit or compute using our numerical solutions the ratio between the axion and cold dark matter as a function of k at redshift 0. This is the transfer function. There is a fit for this transfer function from Wayne Hu's paper. Tk is cos xj cubed over 1 plus xj to the 8, where xj is this function of k over kj evaluated at equality. This function actually only matches the solution from Axion Cam in its first few oscillations, because we asked Wayne Hu and he said, oh yeah, I only fit the results for the first 2 oscillations. So this isn't meant to be, a completely perfect solution, but it fits the shape of the cutoff and the first oscillation in the transfer function. Everything below that you're probably hidden in the lack of structure, but this isn't perfect. This is only fit. So, this leads to a suppression of power for axion dark matter compared to cold dark matter that's somewhat similar to warm dark matter. So axion mass is about 10 to the minus 22 eV, suppress power on scales similar to warm dark matter with a mass of about k eV, just by looking at what kj equality is here and the equivalent transfer function fits for warm dark matter. So I just make that comparison here. So here is that transfer function as a function of wave number for different axion masses. And then the dotted line is the transfer function for warm dark matter where I've chosen the masses such that these functions overlap at transfer function of about 0.5. So my axions come in 10 to minus 23, 22, 21, cut off the power spectrum at wave numbers of order 1, 9, 20, something like that. And these warm dot matter models are masses in the range 0.5 to 5 keV or so. So this is the take-home message from this part of the talk. So we've done how does cosmological perturbation theory work, which will hopefully demystify a bit where the C and B calculations come from in both lectures 6 and 7. But this, for the light axions, is really the important thing in terms of the constraints for structure formation. So light axions depart from standard cold dot matter in their dynamics. The Broglie wavelength, or if you like the quantum pressure, or if you like the sound speed, and suppress the formation of structure relative to cold dot matter. So here is another plot of the matter power spectrum, which we saw before with a load of data on it. Matter power spectrum measures the clustering. It's related to the Fourier transform of the two-point function. Here's the wave number, small k's large, large k's small scales. Galactic halos are forming due to fluctuations at wave numbers of order 1, 0.1 to 1. Here, with fuzzy dark matter, a mass of about 10 to the minus 21 eV, departs strongly from cold dark matter in the linear power spectrum on wave numbers of order 1 to 10. These are, but if I made the axion mass smaller, you would start to affect the formation of galaxies. This is where we're going to get constraints from in lecture 7. And the key to all of this is the Jeans wave number, which here is about 9 inverse megaparsecs times this function of the mass. Okay, so that is all I wanted to tell you today about cosmological perturbation theory. Slightly early finish, but I'm sure we've all had quite a long week anyway. We will start on Monday again with lecture 6 and the cosmic microwave background. As we have stopped a little bit early, are there any questions from anyone about anything we've done all week? So QCD axion models, string theory models, production, initial conditions, cosmological perturbation theory. Any questions at all? Okay, well, see you all on Monday then.